So finally, we turn to the study of quasars and other active galactic nuclei. They represent very interesting phenomena and play an important role in modern cosmology. To define them, these are very energetic events in the cores of certain galaxies. And we believe that energy is being released because of the accretion on black holes that sit there, and the loss of the binding energy for material to get there produces the great release of energy from that is observed. There are empirical classification schemes that describe the properties of active nuclei, and we'll go through these shortly. And more recently, there have been unification schemes designed to explain how various aspects of observed phenomenology may be really the same thing, but observed from different angles. One interesting thing about quasars is that they evolve very strongly in time. As we go deeper in redshift, the numbers increase dramatically between here and now and, say, redshift of 2 by about a factor of 1,000 per co-moving volume. Today, maybe 1/3 of all galaxies show some sort of non-thermal activity in their cores due to the accretion onto a black hole. Most of that is fairly low luminosity. Maybe one galaxy in 10 million locally has really a quasar-like luminosity, but many have much weaker yet still active nuclei. And as we already hinted at when we talked about elliptical galaxies, we now think that most large galaxies, that is non-dwarf galaxies, do harbor a supermassive black hole in their centers, and their formation is closely tied to the formation of galaxies themselves. So here is a cartoon version of what we think an active nucleus looks like. In the middle, there is a massive black hole. Surrounding it is an accretion disk of material that has fallen down the potential well, and it's settled into a disk because it still has some angular momentum, even though it's lost much energy, from which it dribbles slowly into the black hole. The energy that's been released comes from binding energy of material that came from large distances to the nearest proximity of the black hole. Usually, the black holes seem to be rotating, and if there is any magnetic field involved, that will create a jet of material perpendicular to the accretion disk. The jet comes because the magnetic field gets wound tight and accelerates the ionized gas and electrons to relativistic speeds, essentially as a cosmic accelerator. Surrounding the central engine, from which we see continuum emission, is a region of broad emission line clouds. Those are clouds of gas that are moving at speeds of maybe of the order of 1/10 of the speed of light because of the deep potential well near the black hole. And they have characteristic emission lines. And larger yet is a narrow line emission region of gas clouds that have been ionized by emission from the central engine and move at speeds that are more characteristic of Galaxian potential wells. And finally, we think that there is an obscuring torus or disk of dust hiding the central engine from the view from the side. Probably the most important global characteristic of active nuclei is that they seem to emit energy at all different energies, from radio through gamma rays. And unlike stars that tend to have thermal emission usually focused over more or less 1 octave of frequency space, active nuclei span a much broader range of frequencies. Also, they tend to emit at higher energies than most stars. So ultraviolet and hard X-rays are really good ways to find quasars, and stars generally do not emit much in these wavelength regions. Because of that, the colors of quasars, which would be logs of the flux ratios of different band passes, tend to be very different from those of stars, and that provides a means of finding them. This is also very useful when we look at very high redshifts, where the blue light in the rest frame is absorbed by the intergalactic hydrogen. One characteristic thing about active nuclei is that they do have emission lines, strong emission lines in their spectra, which come from ionized gas. The gas is ionized by the ultraviolet and X-ray emission from the central engine. These objects can reach phenomenal luminosities up to maybe 10 to the 15 solar luminosities. A galaxy like the Milky Way might have a luminosity of the order of 10 to the 10 or 10 to the 11 solar luminosities. Quasars can be thousands of times more luminous, and yet that luminosity comes from a region that's smaller than the solar system. They also show a strong variability at all different wavelengths, and the size of the small region dictates the timescales on which that can happen. And if a region is of the order of light hours across, then emission can vary on scales of hours. And even with the most modern state-of-the-art techniques, the central engines are still unresolved, even for the nearest active galaxies. So a lot of what we know about these objects is inferred from a variety of their physical properties that we observe that come from larger radii. And because they tend to be far away at high redshifts, they do not move very much in time, whereas if you have a long enough baseline of observations, you can see most of the stars in the Milky Way having some proper motion. So all of these characteristics have been used as means to discover active galactic nuclei. Most notably, it was the properties of the broadband spectral energy distribution. Here we have on a log-log diagram what the spectra of quasars might look like from radio into the gamma rays. And the first thing you noticed is that they seem to be more or less flat. There is a roughly equal amount of energy being contributed on a broad range of frequencies. Very much unlike stars with black body emission that seems to usually span about a factor of 2 in wavelength, as opposed to many orders of magnitude that's shown here. Some different components are labeled here. They come from different sources of emission. Some are thermal from, say, hot accretion disk. Some are non-thermal from synchrotron electrons or from the jet. We will talk about those in more detail later. And this is what a typical quasar spectrum looks like. There is a strong blue continuum, and superposed on it are strong emission lines. There are broad emission lines, which are Doppler broadened by the motion of the clouds, which can be thousands of kilometers per second, but there are also narrow emission lines, which come from clouds moving further away from the black hole and mostly probing the potential well of the host galaxy, not the black hole itself. You will also notice that many of these lines come from highly ionized species of ions. The notation of Roman numeral after the element's name indicates how many electrons have been removed, -1. So carbon 1 would be neutral carbon, and carbon 4 is carbon that has lost 3 electrons. Magnesium 2 is magnesium that's lost 1 electron, and so on. The square brackets indicate so-called forbidden or semi-forbidden transitions. They're called that way because they're never observed in terrestrial lab conditions, but they are observed in space. And that means that they usually require very low pressure and low density of the gas and very high temperatures, which are easily obtained in cosmic plasmas, but they're very hard to achieve in laboratory. So since their discovery in early 1960s, there have been surveys to find quasars and other active nuclei in a systematic fashion in order to study them and to use them as cosmological probes. At first, radio emission was used. This is how quasars were discovered. More recently, optical surveys based on colors are the dominant way of finding quasars. The one thing to keep in mind is that each of these methods has its own power and its own limitations and its own selection effects. And to really get a complete picture of active galactic nuclear population in the universe, we have to actually approach this as a very panchromatic problem and try to complete surveys on a variety of different wavelengths. X-rays are also a very productive way to find them. Stars are sometimes X-ray sources, but not nearly as luminous as these active nuclei. And great majority of X-ray sources in the sky outside the plane of the Milky Way are active nuclei at some larger redshifts. Nowadays, we have sky surveys that span full range of frequencies from radio through gamma rays, and combining them together provides means of separating these objects, which have spectral energy distributions very much unlike stars, from stars, whereas at pictures they just look like stars, but they're something very different. Today there are well over 100,000 quasars that have been confirmed by actual spectroscopy, most of them coming from the Sloan Digital Sky Survey. But there is over 1 million of additional highly likely quasars that have been selected through their colors and haven't just had spectra taken yet. These come from large modern digital sky surveys. Early on, surveys were not nearly as large, and they might have discovered tens or hundreds of quasars, and they still serve the purpose. The first surveys tended to be done from Palomar Observatory, and they usually denoted with some acronym like P something, or P stands for Palomar. For example, PG is for Palomar Green, after the astronomer who did the survey. PC is for Palomar CCD-based survey, PSS for Palomar Sky Survey, and so on. Many other observatories have participated in this enterprise, notably University of Michigan and Case Western Reserve University have done extensive surveys for emission line objects, as well as Burakan Observatory in Armenia. There have been many compilations of quasars discovered in any which way, from radio through gamma rays through X-rays, and 2 catalogs that have been used through the literature from Hewitt and Burbidge and Veron-Setti. However, today, those heterogeneous compilations are superseded by much more complete, homogeneous, statistically well understood samples. In addition to that, and in partial overlap, there are about 1 million radio sources cataloged so far. Most of those radio sources in the sky are active galactic nuclei. Not all, some of it comes from star formation, and those in our galaxy, of course, come from things like supernova remnants or star-forming regions. But outside the plane of the Milky Way, great majority of them are from active nuclei. Radio sources may or may not have other visible manifestations of central activity. Sometimes only radio is detected, but no obvious signatures in invisible or even X-rays. Some of the more famous radio surveys include those from the Green Bank Observatory in the US, from Parkes in Australia, from VLA, which are called NVSS and FIRST, and many others. An interesting question to ask is how many quasars are there? And so if you count them per unit area on the sky, going down to the limits of traditional sky surveys of the order of 20th magnitude, maybe going a little deeper, 22nd magnitude, they're of the order of 100 quasars per square degree. And if you go to the very limit of observations, which of course we only do over very small areas, we can infer that there are some tens of millions of quasars observable within our horizon. Or roughly speaking, there is 1 quasar for every 1,000 galaxies integrated over all different redshifts. I mentioned the Sloan Quasar Survey, and that was a component of the larger Sloan Digital Sky Survey. They imaged sky in 5 filters. They covered of the order of 1/2 of the sky, maybe a little less. And using ratios of fluxes in these filters, they can separate quasars from stars. Quasars look like stars, that's why they're called quasars. That stands for quasi-stellar object. But of course, they're very different once you take the spectrum. This shows a couple of the color plots of star-like objects found in Sloan Sky Survey. And the big locus that you see in the middle are mostly stars, galactic stars. But all the dots standing away from that locus tend to be quasars that are at different redshifts. So by putting boundaries in a color space like that, and then following up spectroscopically, one can find numerous quasars. And that's how most of them are actually done. Here are some additional plots. Here, in order to avoid crowding by individual dots, the density contours in color space are plotted for most of the stars, and then outlying stars are plotted as dots. Quasars that are being confirmed spectroscopically are indicated as colored points, and their color is representative of the redshift, as you can see. Now, colors are always defined as blue minus red magnitude, and so the lower left corner corresponds to bluer colors, the upper right to the redder colors. And you can see that quasars tend to be bluer than most stars, but sometimes they overlap with some kinds of stars. The other major survey was done by Anglo-Australian Telescope as part of their redshift survey, and it's now called 2QZ survey. That one detected a couple tens of thousands of new quasars in smaller areas than the Sloan, but nevertheless provided another useful sample for statistical studies. And here is an interesting diagram. What they have done here is they plotted all quasar spectra as individual rows in this image, sorted in redshift. And so the luminous ridges that you see correspond to the strong emission lines. And as you increase the redshift, they move to the red, as they should, because of the redshift. And the new lines come in that are normally ultraviolet and not observable in the visible, such as Lyman alpha or carbon 4 and so on. So it's a nice illustration of how there is a smooth distribution and how redshift actually changes the appearance of these spectra. Next, we will talk about classification of active galactic nuclei.